Hey everyone, this is Chapter 3 Review. In this video, we're going to go over how to describe vectors, how to add them, how to find their components, and then projectile motion problems. First, vectors. To describe them, we need a magnitude. The magnitude of the vector is the length or the size of that vector. For example, let's say we have a vector going down, and the velocity is 5 meters per second. So technically, if it's going down, the velocity would be negative 5 meters per second. If we want to find the magnitude of the velocity, we just want the number. So the magnitude of the velocity would just be 5 meters per second. It's the number without the direction. Keep in mind that the word magnitude is always followed by something. You're never just finding the magnitude of nothing. It's always the magnitude of a certain vector. The direction of a vector is specified by an angle. One way is with a positive counterclockwise angle or a negative clockwise angle. For example, let's say you want to describe a vector that has an angle of negative 110 degrees. So that direction, the negative, means that you're going clockwise from the positive x-axis. So if you're going clockwise, you're going past 90. You're going this way, so the vector is somewhere in the third quadrant. So negative is clockwise, and if you were going counterclockwise, that would be a positive angle. Another way to describe the direction of vectors is using the compass angle notation. For this, you want to draw the second direction first. For example, if we want to draw a vector 60 degrees east of north, we're going to draw north first, which is going up here. You can draw a little dashed line. And then we're going to go 60 degrees east of that. If you're going east, you're going to the right of that vector that way. So 60 degrees is approximately this way. This would be 60 degrees. This would be the vector that is 60 degrees east of north. Just FYI, this would be the same thing as 30 degrees north of east. If you go 30 degrees north of east, you would draw the east first, which is the horizontal x-axis, and then you would go 30 degrees up above that, north of that, and that would be the same exact vector direction. Next, how to add vectors using the tip-to-tail method. For this method, if you're adding two vectors, you're going to place the tail of the second vector at the tip of the first vector. So the tip is where the arrow is. If we're adding A and B, we want to put the tail of the second vector, vector B, at the tip of A. So we want to redraw vector B over here so that the tail of B is at the tip of A. The second step is to draw the resultant from the starting to the ending point. We started over here on the left, and we ended at the tip of B to the right. So that would be the resultant going to the right. That's how you add vectors using the tip-to-tail methods. We know we can do this because we know that we can move vectors anywhere we want, and we haven't changed the vector as long as we haven't changed its magnitude and direction. If we're subtracting vectors, what we're doing is we're adding the negative of a vector. We learned that the negative of a vector is that same vector just going in the opposite direction. So if I want to draw a vector negative b, I'm going to draw a vector negative b in the opposite direction as b. And now if I want to do a minus b, I'm going to start with vector a. I'm just going to redraw it over here so that now I have room to add vector negative b at the tip of vector a. That's vector negative b. Now the resultant is going to be from where you start to where you end. That's going to be the resultant, in this case, a minus b. Next is how to find components of vectors. I like to think of vector components as how you get from the beginning point to the ending point of your vector if you can only move horizontally or vertically. The x component is the horizontal part, the y component is the vertical part. We need to be able to describe these vector components using trig functions. So the shortcut that I have is you write down the component that you're looking for. Let's say you're you're looking for the x component. And then you write equal sign, you write down the hypotenuse of that vector, in this case, vector A. Now, if the component that you're looking for is adjacent to the angle, in this case, AX is adjacent to the angle, then you use cosine. If the component that you're looking for is opposite the angle, then you use sine. So that is the trick for writing components of vectors. Don't forget a direction as well. Don't forget that. If the vector is going to the left or downward, that's negative. If the vector is going up or to the right, that's going to be positive. Let's do an example. Find the x component of this vector. When you're finding components, you want to draw them first. So we're going to go up and then over to the left. That's how we get from the starting point to the ending point of this vector. I like to draw these components with arrows. If this is vector B, then the upward component would be by and the horizontal component would be bx. If we're looking for bx, we're going to write down bx. We're going to write down the hypotenuse, which is 200. And then because this bx component is opposite the angle, we're going to use sine. When we plug this in the calculator, we're going to get negative 153.2 meters. Don't forget the negative. Put it over here as well. It's negative because that x component is going to the left. If you can find vector components, then you are ready to add vectors using the analytical method. The first step of adding vectors, let's say that you want to add vectors a plus b plus c. The first step is to find the x and y components of each vector. Now let's say that you've already found the x and y components of each vector and you've written them down in this table. You found them according to the methods in the previous slide. That's the first step. The next step is to add all of the x components separately to get the x component of the resultant. We're going to get -1 when we add all of the x components. Then get the y component of the resultant. We're going to get 8 when we add all of the y components. That's steps 2 and 3. Now, next step, draw our x and our y and our tip to tail. Our x and our y are the x and y components of our resultant vector. So we're going to draw our x going to the left because it's negative. At the tip, we're going to draw our y, which is going up because it's positive. And then we draw a resultant from where we started to where we ended. That way we can visualize the exact quadrant that r is going to be in. Next up, we find the magnitude of the resultant using the Pythagorean theorem. Let's plug in the components squared inside the square root here. So square root of -1 squared plus 8 squared. Don't worry about putting negatives in the calculator because you're squaring them anyway. The negatives will cancel. We're going to get 8.1 over here. And then find the direction. That means finding this theta here. To find theta, we can use the inverse tan of the y component over the x component. Once again, I don't actually put that negative in the calculator. I put all positives. That's going to give me a positive angle, 82.9. If you did put the negative in here, you'd get a negative 82.9 degrees, which would not be accurate because a negative angle we learned would be in that fourth quadrant, but we know our resultant is in the second quadrant. So visualize the angle. It's 82.9 degrees above the negative x-axis, or you can translate this to an angle with respect to the positive x-axis. Go counterclockwise to get that positive angle. Call that angle phi. In this case, it's going to be 180 degrees for the straight line minus the 82.9. That's what phi is going to be. And that's going to give us 97.1 degrees. That's with respect to the positive x-axis. The final topic is projectile motion. Projectile motion is when an object is launched horizontally or at an angle. The most important thing to do is to separate the x and y variables. That means write all of your x and y variables separately, and then we're going to use the kinematic equations. Use them separately for the x and the y direction. Let's look at the cases of projectile motion. First, if a projectile is launched horizontally, what are the givens that we can write down? In the x direction, the x component of the initial velocity is just going to be the initial velocity, whatever is given. The x component of the acceleration is always 0 for projectile motion problems. For the y direction, that y component of the initial velocity is going to be 0 because all of the velocity is horizontal initially. In the y direction, that acceleration is going to be negative 9.8 meters per second squared, always, for all free fall problems and for all projectile motion problems. The second case is when a projectile is launched at an angle. The difference here is going to be with the x and y components of the initial velocity. You're usually going to be given the initial velocity and the angle that touches the x-axis. In this case, the x component will always use the hypotenuse, which is v initial, times the cosine of the angle. As we said, the x component of the acceleration is always 0. The y component of the velocity is going to use sine because that y component is opposite the angle. It would be going up, this one right here. And the y component of the acceleration, we said, is always negative 9.8 meters per second squared. So the most important thing you can do is separate the x and y variables when you write them down. A few other things that you want to know about projectile motion problems. First of all, if you're launched at an angle and you're asked about the maximum height, keep in mind that it's only the velocity in the y direction that is 0 at the peak. The projectile is still moving. The velocity in the x direction never changes. It's not 0 at any time. Only the velocity in the y direction is 0 at the peak. The other thing is for each case, when you are landing, that velocity is not 0. You can see that red arrow going down here. There is some velocity. It has an x and a y component. That velocity is not 0. And then just like with symmetric freefall problems, if you are launched at an angle and you get back to that same height, the time to go up will equal the time to go down, and the initial speed will equal the final speed. The velocities will be different because they are going in different directions. Let's do one example of projectile motion. You throw a ball with a speed of 5 meters per second at an angle of 30 degrees off a 100-meter tall bridge. How long does it take to land? So the first thing is to identify our x and y given variables separately. I like to separate them on my paper, write down everything I know. This was case 2, launched at an angle. We can visualize it here. Second case like this, but it's actually landing below its original height. We said for the x component of the initial velocity, it's going to be the initial velocity, which is 5 times cosine of the angle, which is 30. The y component of the initial velocity is going to be 5 sine of 30, which is equal to 2.5 meters per second. We also know the acceleration in the x is always 0, and in the y, the acceleration is always negative 9.8 meters per second squared. Just like that, we have 4 given variables. What else are we given? The height of the bridge. Now, height is not one of the 5 variables. Remember, the 5 variables, let's say in the y direction, would be delta y, VOY, VFY, AY, and T. But height is very closely related to the displacement. When the ball is going from its initial position to its final position, it's going down by this amount. That would be the delta y, the vertical displacement, which has the same magnitude as the height. The only difference between the displacement and the height in this case is that the displacement is negative because the ball is going down. So it's crucial to write that negative whenever a displacement is negative. Now, we have 3 given variables in the y direction. We're looking for time. So for this problem, we don't even need anything in the x direction. We have 3 out of the 5 and the 1 unknown. We're ready to look for a relevant equation. If you have your equations handy, you can see that it is this second equation here that has all of the variables that we have written down. So we can go ahead and write it down. Delta y equals VOYT plus 1/2 AYT squared. Now, in order to solve for the unknown variable, we actually need to use the quadratic formula. I've done this on the side, and then we can solve for t. You'll get a positive and a negative answer. The positive answer is going to be 4.78 seconds. You know the time has to be positive. Now, if you don't like to use the quadratic formula, I'm not a huge fan myself, what you could do instead is you could find VFY first using the equation that has VFY squared. This one, VFY squared equals VOY squared plus 2AY delta y. Use this equation to find VFY, and then find time using the other equation, VFY equals VOY plus AT. So if you use this method, you do have to use 2 equations to find t, but you don't have to use a quadratic formula, whatever you prefer. And that's it for the Chapter 3 review video.